In this video, we'll be going through force, mass, and weight. Let's get right into it, beginning with force. We can define a force, F, on a body as a product of its mass and its acceleration. This is where you see the familiar F equals ma, which is Newton's second law of motion. Note that F is a resultant force. And I want to emphasize that force can come in various expressions, and so there are many different formulas to calculate them. For example, there are separate formulas for calculating a tension on a string and an exertion force caused by an impact, just to name a few. These are all individual forces that could affect the final resultant force. So if there were several individual forces acting on the same object, you would have to resolve these forces and add them all up. To put it simply, the resultant force is the sum of all the individual forces acting on the same object. As we discussed, F is the resultant force acting on the object, and thus would cause the object to accelerate in the direction of the resultant force. If we have a look at a few graphical examples, we can see a car traveling towards the right with a force of 2 newtons. Here, I again want to remind you that this is a resultant force acting on the car, should there have been air resistance or even friction. And the mass of the car is 8 kilograms. If we wanted to calculate the acceleration of the car, we can rearrange the formula so A becomes a subject, giving us F over m. Now we substitute the values and we have 2 over 8 or 0.25 meters per second squared. Now let's have a look at a similar car. This time we get reintroduced to the double arrows, which indicates the acceleration. The mass of the car is still 8 kilograms and it's accelerating to the right at 4 meters per second squared. We can use the same formula to calculate the resultant force pulling the car by substituting the values of its mass and acceleration. This gives us 8 multiplied by 4, giving us 32 newtons to the right. You can pause the video to check that it all made sense. Using the formula F equals ma, here are a few questions you can have a go at. If a ball of mass 1.5 kilograms is thrown horizontally with a force of 10 newtons, what is the acceleration of the ball? Have a go at it and see if you get the same answer. So the acceleration is 10 over 1.5, giving us 6.7 meters per second squared, to 2 significant figures. Secondly, if a ball of mass 1.5 kilograms is thrown vertically with a force of 15 newtons, what is the initial acceleration of the ball? Would the acceleration of the ball change over time? Again, have a go at it and see if we get the same answers. This is the initial acceleration, and the acceleration changes over time due to gravity. F equals ma will give you the initial acceleration. However, since there's gravity acting on the ball and other opposing forces such as air resistance, it will cause the ball to decelerate. Also, a reminder that acceleration is a vector quantity. Moving on to mass and weight, we can define mass, m, of an object as a scalar quantity, and its physical property will depend on the amount of matter it contains. As for the weight, denoted by the capital W, it is a vector quantity and is the force the object experiences under gravity. This means that the weight of an object can change depending on the gravity. For example, on Mars, the weight of an object of a certain mass would be lower than that on Earth, as the gravitational pull on Mars is much lower. But in any case, the mass of the object will always remain constant. So, we get the formula W equals mg, where m is the mass of the object and g is the gravitational acceleration the object feels. Can you see the resemblance of this equation to F equals ma? Well, W is the resultant force, or F, m is the mass, and g is the gravitational acceleration, or a. This is essentially F equals ma, merely written in more specific terms. It's important to note that in regular conversation, the word weight is largely interpreted to describe a person's mass. But in a precise language, the weight would actually be the product of the person's mass and the acceleration caused by the gravity. These terms can be confusing, so make sure you keep that in mind. Here we have a guy named Son who weighs in at 88 kilograms on Earth, where gravity is 9.81 meters per second squared. What would Son's weight be? Check to see that your answer matches. Okay, now let's imagine Elon Musk invited you on board his SpaceX rocket to see what's happening on Mars. So now you're on Mars and you feel a huge difference in your weight. This is because the gravitational force is much lower on Mars. Going on to question B, on Mars the gravity on its surface is 3.71 meters per second squared. In this case, what would Son's mass be? Check to see if you got the same answer. And now for part C, what is Son's weight on Mars? Check to see that your answers match. I want to emphasize again the differences between weight and mass and their units. A person's mass is measured in kilograms and their weight is the product of their mass and the gravitational force acting on them. This is measured in newtons. Moving on, we have center of mass and center of gravity. We can start off by defining some terms. The center of mass of a body is defined as a single point at which the mass of the body can be considered to be concentrated. The motion of an object can be described as the motion of its center of mass. For example, we consider an object as a point mass when solving Suvat equations. As you may have guessed, it is indicated as a dot as shown on the basketball. Again, we're just showing that this is the center of mass. This is the case for other objects like a block, for example, as shown on the next picture. As you can see, the center of mass is usually at the center of the object. The center of mass will be the center of gravity if the following are true. The density is uniform all throughout the object. And the gravitational field is uniform. For example, where the gravity is constant, like the Earth's surface. In A-level, you'll find that the center of mass is equal to the center of gravity in most cases, so it's usually safe to assume it. There may be a few questions with objects that don't have uniformly distributed weight, but all you have to do is recognize that the weight of the object is non-uniform. They'll rarely ask you to calculate the center of mass. Alright, question 2. Where do you think the centers of mass are for the following objects? You can pause the video and have a go. The centers of mass are in the middle of the object, indicated in the red dots. The grey dotted lines represent some of the lines of symmetry to show the center of the object. This is where the lines of symmetry crosses. This is only true given that the assumptions that we made about uniformity is also true. If the density of the object is uniform, the center of gravity will be at the same position, where the overall weight of the object acts. Therefore, you can assume that the center of gravity is where the overall weight of the object acts. Although gravity acts in all parts of the object, we assume that the gravity acts on these objects at these single points. This is indicated in the downward marked arrow with a W notation. Question 3. What if the density of an object is non-uniform? Let's say, for example, we have a piece of wood and a piece of metal. The two blocks are superglued together to form one single block. Normally, if the object was uniform, we would use the intersecting lines of symmetry to find the center of mass. But since the object is non-uniform, what we find is that the center of mass will shift towards the heavier side. And in this case, it will be towards the metal as it is the heavier of the two materials. We can now mark the weight. Now we have a glass of apple juice and we want to find its center of mass. Just by looking at the cup itself, we can draw the lines of symmetry to find the center of mass as denoted by the green dot. However, there are things like ice, the apple juice, so the center of mass of the entire object shifts downwards. This is because the center of mass shifts towards the heavier side. You won't be asked to calculate how much it shifts by, but you may be required to recognize the principle for multiple choice or follow-up questions. Moving on to question 4, what if the object was irregular? Here we have an L-shaped object but with a uniform density. Firstly, we need to draw a fixed point. Then what we do is find any random point within the object, tie a rope from that point to the fixed point as shown in the diagram. We then let the object hang by the string. The object will shift to match the center of mass as shown in the diagram. What we need to do here now is, from the chosen point in the object, we draw a vertical line downwards from the point. We then pick another point on the object and do the same thing. Tie the random point on the object to the fixed point, let it hang, and draw a vertical line coming downwards. What you will see is that the two lines that you drew will intercept. This is where the center of mass would be, denoted by the red dot. To finish off the question, we can draw the initial L-shaped object, its center of mass with its weight. Note that the center of mass or the center of gravity of an object can be outside of the object. This is true because sometimes one part of the object is heavier than the other, causing the object to shift when hung by a string, just as we explained in question 3. Well, that's it for this video. Thank you for watching. If there are any questions or something you didn't quite understand, don't hesitate to leave a comment below. And for those of you who are on social media, we have a new Leornian TikTok page where we answer exam questions in quick and simple methods to help your revision in a fun way. You can always use it as revision cue cards. Anyways, thank you for watching. Please like and subscribe for more.